Hello everybody and welcome to Module 4. Now in this module of this course, we're going to be talking about neural networks, discussing how neural networks work, a little bit of the math behind them, talking about gradient descent and back propagation, and how information actually flows through the neural network, and then getting into an example where we use a neural network to classify articles of clothing. So I know that was a lot, but that's what we're going to be covering here. Now neural networks are complex. There's kind of a lot of components that go into them, and I'm going to apologize right now because it's very difficult to explain it all at once. What I'm going to be trying to do is kind of piece things together and explain them in blocks, and then at the end, kind of combine everything together. Now I will say, in case any of you didn't watch the beginning of this course, I do have very horrible handwriting, but this is the easiest way to explain things to you guys. So bear with me, I'm sure you'll be able to understand what I'm saying, but it might just be painful to read some of it. Alright, so let's get into it right away and start discussing what neural networks are and how they work. Well, the whole point of a neural network is to provide, classification or predictions for us. So we have some input information, we feed it to the neural network, and then we want it to give us some output. So if we think of the neural network as this black box, we have all this input, right? We give all this data to the neural network. Maybe we're talking about an image, maybe we're talking about just some random data points, maybe we're talking about a data set, and then we get some meaningful output. This is what we're looking at. So if we're just looking at a neural network from kind of the outside, we think of it as this magical black box. We give some input, it gives us some output. And I mean, we could call this black box just some function, right? Where it's a function of the input, maps it to some output. And that's exactly what a neural network does. It takes input and maps that input to some output, just like any other function, right? Just like if you had a straight line like this is a function. This is your line, whatever it is, you're going to say y equals like 4x. Maybe that's your line. You give some input x and it gives you some value y. This is a mapping of your input to your output. All right, so now that we have that down, what is a neural network made up of? Well, a neural network is made up of layers. And remember, we talked about the layered representation of data when we talked about neural networks. So I'm going to draw a very basic neural network. We're going to start with the input layer. Now, the input layer is always the first layer in our neural network, and it is what is going to accept our raw data. Now, what I mean by raw data is whatever data we want to give to the network, whatever we want to classify, whatever our input information is, that's what this layer is going to receive in the neural network. So we can say, these arrows represent our input and they come to our first input layer. So this means, for example, if you had an image, and this image, and I'll just draw one like this, let's say this is our image, and it has all these different pixels, right? All these different pixels in the image, and you want to make a classification on this image. Well, maybe it has a width and a height, and a classic width and height example is 28 by 28. If you had 28 by 28 pixels, and you want to make a classification on this image, how many input neurons do you think you would need in your neural network to do this? Well, this is kind of, a tough question if you don't know a lot about neural networks. If you're predicting for the image, if you're going to be looking at the entire image to make a prediction, you're going to need every single one of those pixels, which is 28 times 28 pixels, which I believe is something like 784. I could be wrong on that number, but I believe that's what it is. So you would need 784 input neurons. Now that's totally fine. That might seem like a big number, but we deal with massive numbers when it comes to computers, so this really isn't that many. But that's an example of how you would use a neural network input layer to represent an image. You would have 784 input neurons, and you would pass one pixel to every single one of those neurons. Now, if we're doing an example where maybe we just have one piece of input information, maybe it's literally just one number, well then all we need is one input neuron. If we have an example where we have 4 pieces of information, we would need 4 input neurons, right? Now this can get a little bit more complicated, but that's the basis that I want you to understand is that, the pieces of input you're going to have, regardless of what they are, you need one input neuron for each piece of that information, unless you're going to be reshaping or putting that information in a different form. Okay, so let's just actually skip ahead and go to now our output layer. So this is going to be our output. Now, what is our output layer? Well, our output layer is going to have as many neurons, and again, the neurons are just representing like a node in the layer, as output pieces that we want. Now, let's say we're doing a classification for images, right? And maybe there's 2 classes that we could represent. Well, there's a few different ways we could design our output layer. What we could do is say, okay, we're going to use one output neuron. This output neuron is going to give us some value. We want this value to be between 0 and 1, and we'll say that's inclusive. Now, what we can do now if we're predicting two classes, say, okay, so if my output neuron is going to give me some value, if that value is closer to 0, then that's going to be class 0. If this value is closer to 1, it's going to be class 1, right? And that would mean when we have our training data, right, and we talked about training and testing data, we'd give our input, and our output would need to be the value 0 or 1, because it's either the correct class, which is 0, right, or the correct class, which is 1. So like our, what am I saying? Our labels for our training data set would be 0 and 1, and then this value on our output neuron would be guaranteed to be between 0 and 1, based on something that I'm going to talk about a little bit later. That's one way to approach it, right? We have a single value, we look at that value, and based on what that value is, we can determine, what class we predicted. And that works sometimes, but in other instances when we're doing classification, what makes more sense is to have as many output neurons as classes you're looking to predict for. So let's say we're going to have, like 5 classes that we're predicting for, and maybe these 3 pieces of input information are enough to make that prediction. Well, we would actually have 5 output neurons, and each of these neurons would have a value between 0 and 1, and the combination, so the sum of every single one of these values, would be equal to 1. Now, can you think of what this means? If every single one of these neurons has a value between 0 and 1, and their sum is 1, what does this look like to you? Well, to me, this looks like a probability distribution. And essentially what's going to happen is we're going to make predictions for how strongly we think our input information is each class. So if we think that it's like class 1, maybe we'll just label these like this, then what we would do is say, okay, this is going to be 0.9, representing 90%. Maybe this is like 0.001, maybe this is 0.05, 0.003, right? You get the point. It's going to add up to 1, and this is a probability distribution for our output layer. So that's a way to do it as well. And then obviously if we're doing some kind of regression task, we can just have one neuron, and that will just predict some value, and we'll define, what we want that value to be. Okay, so that's my example for my output. Now let's erase this, and let's actually just go back to one output neuron, because that's what I want to use for this example. Now, we have something in between these layers, because obviously, we can't just go from input to output with nothing else. What we have here is called a hidden layer. Now, in neural networks, we can have many different hidden layers. We can have, hidden layers that are connecting to other hidden layers, and like we could have hundreds, thousands if we wanted to. For this basic example, we'll use one, and I'll write this as hidden. So now we have our 3 layers. Now, why is this called hidden? The reason this is called hidden is because we don't observe it when we're using the neural network. We pass information to the input layer, we get information from the output layer, we don't know what happens in this hidden layer or in these hidden layers. Now, how are these layers connected to each other? How do we get from this input layer to the hidden layer to the output layer and get some meaningful output? Well, every single layer is connected to another layer with something called weights. Now, we can have different kind of architectures of connections, which means I could have something like this one connects to this connects to this connects to this, and that could be like my connection kind of architecture, right? We could have another one where this one goes here, and maybe this one goes here, and actually, after I've drawn this line, now we get what we're going to be talking about a lot, which is called a densely connected neural network. Now, a densely connected neural network, or a densely connected layer, essentially means that it is connected to every node from the previous layer. So in this case, you can see every single node in the input layer is connected to every single node in the output layer, or in the hidden layer, my bad. And these connections are what we call weights. Now, these weights are actually what the neural network is going to change and optimize to determine the mapping from our input to our output. Because again, remember, that's what we're trying to do. We have some kind of function, we give some input, it gives us some output. How do we get that input and output? Well, by modifying these weights. Now, it's a little bit more complex, but this is the starting. So these lines that I've drawn are really just numbers, and every single one of these lines is some numeric value. Typically, these numeric values are between 0 and 1, but they can be large, they can be negative. It really depends on what kind of network you're doing and how you've designed it. Now, let's just write some random numbers. So we have like 0.1, this could be like 0.7. You get the point, right? We just have numbers for every single one of these lines, and these are what we call the trainable parameters that our neural network will actually tweak and change as we train to get the best possible result. So we have these connections. Now our hidden layer is connected to our output layer as well. This is again another densely connected layer, because every layer every neuron from the previous layer is connected to every neuron from the next layer. If you would like to determine how many connections you have, what you can do is say there's 3 neurons here, there's 2 neurons here, 3 times 2 equals 6 connections. That's how that works from layers, and then obviously you can just multiply all of the neurons together as you go through and determine what that's going to be. Okay, so that is how we connect these layers. We have these weights. So let's just write a W on here so we remember that those are weights. Now we also have something called biases. So let's add a bias here. I'm going to label this B. Now biases are a little bit different than these nodes we have regularly. There's only one bias, and a bias exists in the previous layer to the layer that it affects. So in this case, what we actually have is a bias that connects to each neuron in the next layer from this layer, right? So it's still densely connected, but it's just a little bit different. Now notice that this bias doesn't have an arrow beside it because this doesn't take any input information. This is another trainable parameter for the network. And this bias is just some constant numeric value that we're going to connect to the hidden layer so that we can do a few things with it. Now these weights always have a value of 1. We're going to talk about why they have a value of 1 in a second, but just know that whenever a bias is connected to another layer or to another neuron, its weight is typically 1. Okay, so we have that connected, we have our bias, and that actually means we have a bias here as well, and this bias connects to this. Notice that our biases do not connect with each other. The reason for this, again, is they're just some constant value, and they're just something we're kind of adding into the network as another trainable parameter that we can use. Now, let's talk about how we actually pass information through the network and why we even use these weights and biases and what they do. So, let's say we have, I can't really think of a good example, so we're just going to do some arbitrary stuff. Let's say we have like data points, right? X, Y, Z. And all of these data points have some mapped value, right? There's some value that we're looking for them, or there's some class we're trying to put them in. Maybe we're clustering them between like red dots and blue dots. So let's do that. Let's say an XYZ is either a part of the red class or the blue class. Let's just do that. So what we want this output neuron to give us is red or blue. So what I'm going to do is say, since it's just one class, we'll get this output neuron in between the range 0 and 1. We'll say, okay, if it's closer to 0, that's red. If it's closer to 1, that's blue. And that's what we'll do for this network and for this example. Now our input neurons are going to obviously be X, Y, and Z. So let's pick some data point, and let's say we have, the value 2, 2, 2. That's our data point, and we want to predict whether it's red or blue. How do we pass it through? Well, what we need to do is determine how we can, find the value of this hidden layer node. We already know the value of this input node, but now we need to go to the next layer using these connections and find what the value of these nodes are. Well, the way we determine these values is I'm going to say, and I've just said N1 just to represent like this is a node, like this is node 1, maybe this one should be node 2, is equal to what we call the weighted sum of all of the previous nodes that are connected to it, if that makes any sense to you guys. So a weighted sum is something like this. So I'm just going to write the equation and I'll explain it. I'm going to say N1 is equal to the sum of, let's not say N equals 0. Let's say I equals 0 to N of, in this case, we're going to say Wi times Xi plus B. Now, I know this equation looks really mathy and complicated. It's really not. What this symbol and this equation here means is take the weighted sum of all the neurons that are connected to this neuron. So in this case, we have neuron X, neuron Y, and neuron Z connected to N1. So when we take the weighted sum, or we calculate this, what this is really equal to is the weight at neuron X, so we can say Wx, times the value at neuron X, which in this case is just equal to 2, right? Plus whatever the weight is at neuron Y, so in this case this is Wy, and then times 2, and then you get the point where we have Wz, and I'm trying on the edge of my drawing tablet to write this, times 2. Now obviously these weights have some numeric value. Now when we start our neural network, these weights are just completely random. They don't make any sense, they're just some random values that we can use. As the neural network gets better, these weights are updated and changed to make more sense in our network. So right now we'll just leave them as Wx, Wy, Wz, but know these are some numeric values. So this returns to a sum value, right? Some value, let's just call this value V, and that's what this is equal to, so V. Then what we do is we add the bias. Now remember, the bias was connected with a weight of 1, which means if we take the weighted sum of the bias, right, all we're doing is adding whatever that bias's value was. So if this bias value was 100, then what we do is we add 100. Now I've just written the plus b to explicitly state the fact that we're adding the bias, although it could really be considered as a part of this summation equation because it's another connection to the neuron. Now let's just talk about what this symbol means for anyone that's confused about that. Essentially this stands for sum, I stands for an index, and n stands for what index we'll go up to. Now n means how many neurons we had in the previous layer, and then what we're doing here is saying wi(xi), so we're going to say weight 0, x0 plus weight 1, x1 plus weight 2, x2. It's almost like a for loop where we're just adding them all together, and then we add the b. And I hope that makes enough sense so that we understand that. So that is our weighted sum and our bias. So essentially what we do is we go through and we calculate these values. So this gets some value, maybe this value is like 0.3, maybe this value is 7, whatever it is, and we do the same thing now at our output neuron. So we take the weighted sum of this value times its weight, and then we take the weighted sum, so this value times its weight, plus the bias. This is given some value here, and then we can look at that value and determine what the output of our neural network is. So that is pretty much how that works in terms of the weighted sums, the weights, and the biases. Now let's talk about the kind of the training process and another thing called an activation function. So I've lied to you a little bit because I've said, I'm just going to start erasing some stuff so we have a little bit more room on here. So I've lied to you and I've said that this is completely how this works. Well, we're missing one key feature that I want to talk about, which is called an activation function. Now remember how we want this value to be in between 0 and 1, right, at our output layer. Well, right now, we can't really guarantee that that's going to happen. I mean, especially if we're starting with random weights and random biases in our neural network, and we're passing this information through, we could get to this, point here, and we could have like 700 as our value. That's kind of crazy to me, right? We have this huge value. How do we look at 700 and determine whether this is red or whether this is blue? Well, we can use something called an activation function. Now I'm going to go back to my slides here, whatever we want to call this notebook, just to talk about what an activation function is. And you guys can see here, you can follow along. I have all the equations kind of written out here as well. So let's go to activation function, which is right here. Okay. So these are some examples of an activation function, and I just want you to look at what they do. So this first one is called rectify linear unit. Now notice that essentially what this activation function does is take any values that are less than 0 and just make them 0. So any x values that are, in the negative, it just makes their y 0. And then any values that are positive, it's just equal to whatever their positive value is. So if it's 10, it's 10. This allows us to just pretty much eliminate any negative numbers, right? That's kind of what rectify linear unit does. Now tan h, or hyperbolic tangent. What does this do? This actually squishes our values between -1 and 1. So it takes whatever values we have, and the more positive they are, the closer to 1 they are. The more negative they are, the closer to -1 they are. So can we see why this might be useful, right, for our neural network? And then last one is sigmoid. What this does is squish our values between 0 and 1. A lot of people call it like the squishifier function because all it does is take any extremely negative numbers and put them closer to 0, and any extremely positive numbers and put them close to 1. Any values in between, you're going to get some number that's kind of in between that based on the equation 1 over 1 plus e to the negative z. And this is theta z, I guess, is equal to that. Okay, so that's how that works. Those are some activation functions. Now, I hope that's not too much math for you, but let's talk about how we use them, right? So essentially what we do is at each of our neurons, we're going to have an activation function that is applied to the output of that neuron. So we take this weighted sum plus the bias, and then we apply an activation function to it before we send that value to the next neuron. So in this case, n1 isn't actually just equal to this. What n1 is equal to is n1 is equal to f, which stands for our activation function of this equation, right? So say I equals 0, wi xi plus b, and that's what n1's value is equal to when it comes to this output neuron. So each of these have an activation function on them. N2 has the same activation function as N1, and we can define what activation function we want to apply at each neuron. Now at our output neuron, the activation function is very important because we need to determine what we want our value to look like. Do we want it between -1 and 1? Do we want it between 0 and 1? Or do we want it to be some massively large number? Do we want it between 0 and positive infinity? What do we want, right? So what we do is we pick some activation function for our output neuron, and based on what I said, where we want our values between 0 and 1, I'm going to be picking the sigmoid function. So sigmoid, recall, squishes our values between 0 and 1. So what we'll do here is we'll take n1, right? So n1 times whatever the weight is there, so weight 0, plus n2 times weight 1, plus a bias, and apply sigmoid. And then this will give us some value between 0 and 1. Then we can look at that value and we can determine what the output of this network is. So that's great, and that makes sense why we would use that on the output neuron, right? So we can squish our value in between some kind of value so we can actually look at it and determine, what to do with it rather than just having these crazy, and I want to see if I can make this eraser any bigger. That's much better. Okay. So there we go. Let's just erase some of this. And now let's talk about why we would use the activation function on like an intermediate layer like this. Well, the whole point of an activation function is to introduce complexity into our neural network. So essentially, we just have these basic weights and these biases, and this is kind of just, like a complex function at this point. We have a bunch of weights, we have a bunch of biases, and those are the only things that we're training and the only things that we're changing to make our network better. Now, what an activation function can do is, for example, take a bunch of points that are on the same plane, right? So let's just say these are in some plane. If we can apply an activation function of these where we introduce a higher dimensionality, so an activation function like sigmoid that is like a higher dimension function, we can hopefully spread these points out and move them up or down off the plane in a hopes of extracting kind of some different features. Now, it's hard to explain this until we get into the training process of the neural network, but I'm hoping this is maybe giving you a little bit of idea. If we can introduce a complex activation function into this kind of process, then it allows us to make some more complex predictions. We can pick up on some different patterns. If I can see that, when sigmoid or rectify linear unit is applied to this output, it moves my point up, or it moves it down, or it moves it in whatever direction in n-dimensional space, then I can determine specific patterns I couldn't determine in the previous dimension. That's just like if we're looking at something in 2 dimensions, if I can move that into 3 dimensions, I immediately see more detail. There's more things that I can look at, right? And I'll try to do a good example of why we might use it like this. So let's say we have a square, right? Like this, right? And I ask you, I'm like, tell me some information about this square. Well, what you can tell me immediately is you can tell me the width, you can tell me the height, and I guess you could tell me the color, right? You can tell me it has 1 face, you can tell me it has 4 vertexes, you can tell me a fair amount about the square, you can tell me its area. Now, what happens as soon as I extend this square and I make it into a cube? Well, now you can immediately tell me a lot more information. You can tell me, the height, or I guess the depth, width, height, depth, yeah, whatever you want to call it there. You can tell me how many faces it has. You can tell me what color each of the faces are. You can tell me how many vertexes. You can tell me if this cube or this square or this rectangle is uniform or not. And you can pick up on a lot more information. So that's kind of, this is a very oversimplification of what this actually does, but this is kind of the concept, right? Is that if we are in 2 dimensions, if we can somehow move our data points into a higher dimension by applying some function to them, then what we can do is get more information and extract more information about the data points, which will lead to better predictions. Okay, so now that we've talked about all this, it's time to talk about how neural networks train, and I think you guys are ready for this. This is a little bit more complicated, but again, it's not that crazy. All right, so we talked about these weights and biases, and these weights and biases are what our network will come up with and determine to, make the network better. So essentially, what we're going to do now is talk about something called a loss function. So as our network starts, right, the way that we train it, just like we've trained other networks or other machine learning models, is we give it some information, we give it what the expected output is, and then we just see what the expected output, or what the output was from the network, compare it to the expected output, and modify it like that. So essentially what we start with is we say, okay, 222, we say this class is red, which I forget what I labeled that as, but let's just say like that was a 0, okay? So this class is 0. So I want this network to give me a 0 for the point 222. Now this network starts with completely random weights and completely random biases. So chances are when we get to this output here, we're not going to get 0. Maybe we get some value after applying the sigmoid function that's like 0.7. Well, this is pretty far away from red. But how far away is it? Well, this is where we use something called the loss function. Now what a loss function does is calculate how far away our output was from our expected output. So if our expected output is 0 and our output was 0.7, the loss function is going to give us some value that represents like how bad or how good this network was. Now, if it tells us this network was really bad, it gives us like a really high loss, then that tells us that we need to tweak the weights and biases more and move the network in a different direction. We're starting to get into gradient descent, but let's understand the loss function first. So it's going to say if it was really bad, let's move it more, let's change the weights more drastically, let's change the biases more drastically. Whereas if it was really good, it'll be like, okay, so that one was actually decent. You know, you only need to tweak a little bit and you only need to move this, this, and this. So that's good. And that's the point of this loss function. It just calculates some value. The higher the value, the worse our network was. A few examples of a loss function. Let's go down here because I think I had a few. Optimizer, loss, here. Mean squared error, mean absolute error, and hinge loss. Now, mean absolute error, you know what? Let's actually just look one up here. So, mean absolute error. And have a look at what this is. So, images, let's pick something. This is mean absolute error. This is the equation for mean absolute error. Okay, so the summation of the absolute value of yi minus lambda of xi over n. Now, this is kind of complicated. I'm not going to go into it too much. I was hoping I was going to get like a better example for mean squared error. Okay, so these are the three loss functions here. So mean squared error, mean absolute error, hinge loss. Obviously, there's a ton more that we could use. I'm not going to talk about how each of these work specifically. I mean, you can look them up pretty easily. And also, so you know, these are also referenced as cost functions, so cost or loss. You might hear these terms kind of interchanged. Cost and loss essentially mean the same thing. You want your network to cost the least. You want your network to have the least amount of loss. Okay, so now that we have talked about the loss function, we need to talk about how we actually update these weights and biases. Now, let's go back to here because I think I had some notes on it. This is what we call gradient descent. So essentially, the parameters for our network are weights and biases. And by changing these weights and biases, we will, you know, either make the network better or make the network worse. The loss function will determine if the network is getting better, if it's getting worse, and then we can determine how we're going to move the network to change that. So this is now gradient descent, where the math gets a little bit more complicated. So this is an example of what your neural network function might look like. Now, as you have higher dimensional math, you have, you know, a lot more dimensions, a lot more space to explore when it comes to creating different parameters and creating different biases and activation functions and all of that. So as we apply our activation functions, we're kind of spreading our network into higher dimensions, which just makes things much more complicated. Now, essentially what we're trying to do with the neural network is optimize this loss function. This loss function is telling us how good it is or how bad it is. So if we can get this loss function as low as possible, then that means we should technically have the best neural network. So if this is our kind of loss functions like mapping or whatever, what we're looking for is something called a global minimum. We're looking for the minimum point where we get the least possible loss from our neural network. So if we start where these red circles are, right, and I've just stole this image off Google Images, what we're trying to do is move downwards into this global minimum. And this is what the process of called gradient descent. So we calculate this loss, and then we use an algorithm called gradient descent, which tells us what direction we need to move our function to determine or to get to this global minimum. So it essentially looks where we are. It says this was the loss, and it says, okay, I'm going to calculate what's called a gradient, which is literally just a steepness or a direction, and we're going to move in that direction. And then the algorithm called back propagation will go backwards through the network and update the weights and biases so that we move in that direction. Now, I think this is as far as I really want to go because I know this is getting more complicated already than some of you guys probably can handle and that I can probably explain. But that's kind of the basic principle. We'll go back to the drawing board and we'll do a very quick recap before we get into some of the other stuff. Neural networks: input, output, hidden layers. Connected with weights, there's biases that connect to each layer. These biases can be thought of as y-intercepts. They'll simply move completely up or move completely down that entire, activation function, right? We're just shifting things left or right because this will allow us to get a better prediction and have another parameter that we can train and add a little bit of complexity to our, neural network model. Now, the way that information is passed through these layers is we take the weighted sum at a neuron of all of the connected neurons to it. We then add this bias neuron and we apply some activation function that's going to put this, between -1 and 1, and then we continue the process. So N1 gets its value, N2 gets its value, and then we know we are class Y or we are class. Essentially what happens, a gradient is the direction we need to move through the network and update, likely, unless we're overfitting. But if we have a lot of data, if we can keep feeding the network, it starts off being really horrible, having no idea what's going on. Better, we got an 85% accuracy, and that into the map for our network allows us to shift this kind of activation function left, right, up, down, and yeah, that is how that works. Okay, so now we have an optimizer. This is kind of the last thing on how neural networks work. Optimizer is literally just the algorithm that does the gradient descent and back propagation for us. So I mean, you guys can read through some of them here. We'll be using probably the Atom optimizer for most of our examples, although there's lots of different ones that we can pick from. Now this optimization technique, again, is just a different algorithm. There's some of them are faster, some of them are slower, some of them work a little bit differently, and we're not really going to get into picking optimizers in this course because that's more of an advanced machine learning technique. All right, so enough explaining, enough math, enough drawings, enough talking. Now it is time to create our first official neural network. Now, these are the imports we're going to need. So import TensorFlow as TF, from TensorFlow import Keras. Again, so this does actually come with TensorFlow. I forget if I said you need to install that before. My apologies. And then import NumPy as NP, import matplotlib.pyplot as PLT. All right, so I'm going to do actually a similar thing to what I did before, where I'm kind of just going to copy some of this code into another notebook just to make sure that we can look at everything at the end, and then kind of step through the code step by step rather than all of the text kind of happening here. All right, so the data set and the problem we are going to consider for our first neural network is the fashion-MNIST dataset. Now, the fashion-MNIST dataset contains 60,000 images for training and 10,000 images for validating and testing, 70,000 images, and it is essentially pixel data of clothing articles. So what we're going to do to load in this data set from Keras, so this is actually built into Keras, it's meant as like a beginner like testing training data set. We're going to say fashion_MNIST equals keras.datasets.fashion_MNIST. Now this will get the dataset object, and then we can load that object by doing fashion_MNIST.loadData. Now by doing this, by having the tuples train images, train labels, test images, test labels equals this will automatically split our data into the sets that we need. So we need the training and we need the testing. And again, we've talked about all of that, so I'm going to kind of skim through that. And now we have it in all of these kind of tuples here. All right, so let's have a look at this data set to see what we were working with. Okay, so let's run some of this code. Let's get this import going if it doesn't take forever. Okay, let's get the data set. Yeah, this will take a second to download for you guys if you don't already have it cached. And then we'll go train images.shape, and let's look at what one of the images looks like. Or sorry, what our data set looks like. So we have 60,000 images that are 28 by 28. Now what that means is we have 28 pixels, or 28 rows of 28 pixels, right? So that's kind of what our information is. So we're going to have in total 784 pixels, which I've denoted here. So let's have a look at one pixel. So to reference one pixel, this is what I'm doing. This comes in as a, actually, I'm not sure what type of data frame this is, but let's have a look at it. So let's say type of train_images, because I want to see that. So it's an NumPy array. So to reference the different indexes in this, it's similar to pandas, we're just going to do 0, 23, 23, which stands for, you know, image 0, 23, and then 23, and this gives us 1 pixel. So row 23, column 23, which will be that. Okay, so let's run this, and let's see, this value is 194. Okay, so that's kind of interesting. That's what 1 pixel looks like. So let's look at what multiple pixels look like. So we'll print train underscore images. And okay, so we get all these zeros. Let's print train images 0 colon. That should work for us. And we're getting all these zeros. Okay, so that's the border of the picture. That's, okay, I can't show you what I wanted to show you. Anyways, 1 pixel, and I wanted to have you guys guess it, is simply just represented by a number between 0 and 255. Now what this stands for is the grayscale value of this pixel. So we're dealing with grayscale images, although we can deal with, you know, 3D, 4D, 5D images as well, or not 5D images, but we can deal with images that have like RGB values. So for example, we could have a number between 0 and 255, another number between 0 and 255, and another number between 0 and 255 for every single pixel, right? Whereas this one is just one simple static value. Okay, so it says that here our pixel values between 0 and 255, 0 being black and 255 being white. So essentially, you know, if it's 255, that means that this is white. If it's 0, that means that it is black. All right, so let's have a look at the first 10 training labels. So that was our training images. Now what are the training labels? Okay, so we have an array and we get values from 0 to 9. Now this is because we have 10 different classes that we could have for our data set. So there's 10 different articles of clothing that are represented. I don't know what all of them are, although they are right here. So t-shirt, trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, ankle boot. Okay, so let's run this class names just so that we have that saved. And now what I'm going to do is just use matplotlib to show you what one of the images looks like. So in this case, this is a shirt. I know this is printing out kind of weird, but I'm just showing the image. I know it's like different colors, but that's because if we don't define that we're drawing at grayscale, it's going to do this. But anyways, that is what we get for the shirt. So let's go to another image and let's have a look at what this one is. I actually don't know what that is, so we'll skip that. Maybe that's a, what is it, t-shirt or top. This, I guess, is going to be like a dress. Yeah, so we do have dress there. Let's go have a look at this. And some of these are like hard to even make out when I'm looking at them myself. And then I guess this will be like a hoodie or something. I'm trying to get one that's a sandal to show you guys a few different ones. There we go. So that is a sandal or a sneaker. Okay, so that is kind of how we do that and how we look at the different images. So if you wanted to draw it out, all you do is just make a figure. You just show the image, do the color bar, which is just giving you this. Then you're going to say, I don't want a grid, and then you can just show the image, right? Because if you don't have this line here and you show with the grid, oh, it's actually not showing the grid. That's interesting. Although I thought it was going to show me those pixelated grids. So I guess you don't need that line. All right, so data pre-processing. All right, so this is an important step in neural networks. And a lot of times when we have our data, we have it in these like random forms, or we're missing data, or there's information we don't know, or that we haven't seen. And typically what we need to do is pre-process it. Now what I'm going to do here is squish all my values between 0 and 1. Typically, it's a good idea to get all of your input values in a neural network in between like that range. In between, I would say -1 and 1 is what you're trying to do. You're trying to make your numbers as small as possible to feed to the neural network. The reason for this is your neural network starts out with random weights and biases that are in between the range 0 and 1, unless you change that value. So if you have massive input information and tiny weights, then you're kind of having a bit of a mismatch, and you're going to make it much more difficult for your network to actually classify your information, because it's going to have to work harder to update those weights and biases to reduce how large those values are going to be, if that makes any sense. So it usually is a good idea to pre-process these and make them in between the value of 0 and 1. Now, since we know that we're just going to have pixel values that are in the range of 255, we can just divide by 255, and that will automatically scale it down for us. Although it is extremely important that we do this to not only the training images, but the testing images as well. If you just pre-process your training images and then you pass in, new data that's not pre-processed, that's going to be a huge issue. You need to make sure that your data comes in the same form, and that means when we're using the model to make predictions, whatever, I guess pixel data we have, we need to pre-process in the same way that we pre-processed our other data. Okay, so let's pre-process that. So train images and test images, and I'm just going to actually steal some of this stuff here and throw it in my other one before we get too far. So let's get this data set and let's throw it in here just so we can come back and reference all of this together. Let's go class names. We don't actually need the figure. There's a few things I can skip. We do need this pre-processing step like that. If I could go over here. And then what else do we need? We're going to need this model. Okay, so let's actually just copy the model into this and just make it a little bit cleaner. We can have a look at it. So new code block model. Okay, so model. Creating our model. Now, creating our model is actually really easy. I'm hoping what you guys have realized so far is that data is usually the hardest part of machine learning and neural networks. Getting your data in the right form, the right shape, and pre-processed correctly. Building the model is usually pretty easy because we have tools like TensorFlow and Keras that can do it for us. So we're going to say model equals keras.sequential. Now, sequential simply stands for the most basic form of neural network, which we've talked about so far, which is just information going from the left side to the right side, passing through the layers sequentially, right? Called sequential. We have not talked about recurrent or convolutional neural networks yet. Now, what we're going to do here is go keras.layers.flatten. So sorry, inside here, we're going to define the layers that we want in our neural network. This first layer is our input layer, and what flatten does is allows us to take in a shape of 28 by 28, which we've defined here, and flatten all of the pixels into 784 pixels. So we take this 28 by 28 kind of matrix-like structure and just flatten it out. And Keras will do that for us. We don't actually need to take our matrix data and transform it before passing. So we've done that. Next we have keras.layers.dense 128 activation equals rectify linear unit. So this is our first hidden layer, layer 2, right? That's what I've denoted here. And this is a dense layer. Now, dense again means that all of the the neurons in the previous layer are connected to every neuron in this layer. So we have 828 neurons here. How do we pick that number? We don't know. We kind of just came up with it. Usually it's a good idea that you're going to do this as like a little bit smaller than what your input layer is, although sometimes it's going to be bigger, sometimes it's going to be half the size. It really depends on the problem. I can't really give you a straight answer for that. And then our activation function will define as rectify linear unit. Now we could pick a bunch of different activation functions. There's a ton. We could pick sigmoid, we could pick tanh, which is hyperbolic tangent. Doesn't really matter. And then we're going to define our last layer, which is our output layer, which is a dense layer of 10 output neurons with the activation of softmax. Okay, so can we think of why we would have picked 10 here, right? I'll give you guys a second to think about it, based on the fact that our output layer, is supposed to have as many neurons as classes we're going to predict for. So that is exactly what we have 10. If we look, we have 10 classes here. So we're going to have 10 output neurons in our output layer. And again, we're going to have this probability distribution, and the way we do that is using the activation function softmax. So softmax will make sure that all of the values of our neurons add up to 1 and that they're between 0 and 1. So that is our model. We've created the model now. So let's actually run this. Let's see, are we going to get any errors here, or is this going to run? And then we'll run the model, and then we'll go on to the next step, which is actually going to be training and testing the model. Okay, so let's create the model now. Shouldn't get any issues, and we're good. And now let's move on to the next step. I'm forgetting what it is, though, which is training the model. Oh, sorry, compiling the model. Okay, so compiling the model. So we've built now what we call the architecture of our neural network, right? We've defined the amount of neurons in each layer, we've defined the activation function, and we've defined the type of layer and the type of connections. The next thing we need to pick is the optimizer, the loss, and the metrics we're going to be looking at. So the optimizer we're going to use is Atom. This is, again, just the algorithm that performs the gradient descent. You don't really need to look at these too much. You can read up on some different activation functions, or optimizers, if you want to kind of see the difference between them, but it's not crazy. We're going to pick a loss. So in this case, sparse categorical cross entropy. Again, not going to go into depth about that. You guys can look that up if you want to see how it works. And then metrics. So what we're looking for, the output that we want to see from the network, which is accuracy. Now from, kind of right now with our current knowledge, we're just going to stick with this as what we're going to compile our neural networks with. We can pick different values if we want, and these are what we call, hyperparameter tuning. So the parameters that are inside here, so like the weights and the biases, are things that we can't manually change, but these are things that we can change, right? The optimizer, the loss, the metrics, the activation function, we can change that. So these are called hyperparameters. Same thing with the number of neurons in each layer. So hyperparameter tuning is a process of changing all of these values and looking at how models perform with different hyperparameters change. So I'm not really going to talk about that too much, but that is something to note because you'll probably hear that, this hyperparameter kind of idea. Okay, so we've compiled the model now using this, which just means we've picked all the different things that we need to use for it. And now on to training the model. So I'm just going to copy this in. Again, remember these parts are pretty syntactically heavy, but fairly easy to actually do. So we're going to fit the model. So fit just means we're fitting it to the training data. It's another word for training, essentially. So we're going to pass it the training images, the training labels, and notice how much easier it is to pass this now. We don't need to do this input function. We don't need to do all of that because Keras can handle it for us, and we define our epochs as 10. Epochs is another hyperparameter that you could tune and change if you wanted to. All right, so that will actually fit our model. So what I'm going to do is put this in another code block so I don't need to keep retraining this. So we'll go like that. And let's actually look at this training process. So we've run the model. This should compile, and now let's fit it and let's see what we actually end up getting. All right, so epoch 1, and we can see that we're getting a loss and we're getting accuracy printing out on the side here. Now this is going to take a second. Like this is going to take a few minutes as opposed to our other models that we made, or not a few minutes, but a few seconds. When you have 60,000 images and you have a network that's comprised of 784 neurons, 128 neurons, and then 10 neurons, you have a lot of weights and biases and a lot of math that needs to go on. So this will take a few seconds to run. Now, if you're on a much faster computer, you'll probably be faster than this. But this is why I like Google Collaboratory, because, this isn't using any of my computer's resources to train. It's using this. And we can see, like, the RAM and the disk. How do I look at this? In this network. Oh, is it going to let me look at this now? Okay, I don't know why it's not letting me click this, but usually you can have a look at it. And now we've trained and we've fit the model. So we can see that we had an accuracy of 91%. But the thing is, this is the accuracy on our testing or our training data. So now if we want to find what the true accuracy is, what we need to do is actually test it on our testing data. So I'm going to steal this line of code here. This is how we test our model. Pretty straightforward. I'll just close this. So let's go a new code block. So we have test loss, test accuracy is model.evaluate, test images, test labels, verbose equals 1. Now, what is verbose? I was hoping it was going to give me the thing so I could just read it to you guys, but verbose essentially is just, are we looking at output or not? So like how much information are we seeing as this model evaluates? It's like how much is printing out to the console. That's what that means. And yes, this will just split up kind of the metrics that are returned to this into test loss and test accuracy so we can have a look at it. Now you will notice when I run this that the accuracy will likely be lower on this than it was on our model. So actually the accuracy we had from this was about 91, and now we're only getting 88.5. So this is an example of something we call overfitting. Our model seemed like it was doing really well on the testing data, or sorry, the training data, but that's because it was seeing that data so often, right? With 10 epochs, it started to just kind of memorize that data and get good at seeing that data. Whereas now when we pass it new data that it's never seen before, it's only 88.5% accurate, which means we overfit our model and it's not as good at generalizing for other data sets, which is usually the goal, right? When we create a model, we want the highest accuracy possible, but we want the highest accuracy possible on new data. So we need to make sure our model generalizes properly. Now in this instance, you know, it's hard to figure out how do we do that because we don't know that much about neural networks, but this is the idea of overfitting and of hyperparameter tuning, right? So if we can start changing some of this architecture and we can change maybe the optimizer, the loss function, maybe we go epochs 8, let's see if this does any better, right? So let's now fit the model with 8 epochs. We'll have a look at what this accuracy is, and then we'll test it and see if we get a higher accuracy on the testing data set. And this is kind of the idea of that hyperparameter tuning, right? Where we just look at each epoch, or not each epoch, we look at each parameter, we tweak them a little bit, and usually we'll like write some code that automates this for us. But that's the idea, is we want to get the most generalized accuracy that we can. So I'll wait for this to train. We're actually almost done, so I won't even bother cutting the video. And then we'll run this evaluation and we'll see now if we got a better accuracy. Now I'm getting a little bit scared because the accuracy is getting very high here. And sometimes, you know, like you want the accuracy to be high on your training data, but when it gets to a point where it's very high, you're in a situation where it's likely that you've overfit. So let's look at this now and let's see what we get. So 88.4. So we actually dropped down a little bit and it seemed like those epochs didn't make a big difference. So maybe if I train it on one epoch, let's have an idea and see what this does. You know, make your prediction. Do you think we're going to be better? Do you think we're going to be worse? It's only seen the training data one time. Let's run this and let's see 89.34. So in this situation, less epochs was actually better. So that's something to consider. You know, a lot of people I see just go like 100 epochs and just think their model is going to be great. That's actually not good to do. A lot of the times you're going to have a worse model because what's going to end up happening is it's going to be seeing the same information so much, tweaking so specifically to that information that it's seen, that when you show it new data, it can't actually, you know, classify and generalize on that. All right, so let's go back and let's see what else we're doing now with this. Okay, so now that we've done that, we need to make predictions. So to make predictions is actually pretty easy. So I'm actually just going to copy this line in. We'll go into a new code block down here. So all you have to do is say model.predict, and then you're going to give it an array of images that you want to predict on. So in this case, if we look at test images shape, so actually let's make a new code block and let's go here. So let's say test underscore images dot shape. All right, give me a second. So we have 10,000 by 28 by 28. So this is an array of 10,000 entries of images. Now, if I just wanted to predict on one image, what I could do is say test images 0 and then put that inside of an array. The reason I need to do that is because the data that this model is used to seeing is an array of images to make a prediction on. That's what this predict method needs, and it's much better at making predictions on many things at once than just one specific item. So if you are predicting one item only, you do need to put it in an array because it's used to seeing that form. So we could do this. I'm just going to leave it, so we're just going to predict on every single one of the test images, because then we can have a look at a cool function I've kind of made. So let's actually do this. Predictions equals model.predict test images. Let's print predictions and look at actually what it is. Where is my autocomplete? There it is. Okay. So let's have a look. Is this some object? Whoa. Okay. So this is arrays of arrays that looks like we have some like really tiny numbers in them. So what this is essentially every single, prediction, or every single image has a list that represents the prediction for it, just like we've done with kind of the linear models and stuff like that. So if I want to see the prediction for test image 0, I would say prediction 0, right? Let's print this out. And this is the array that we're getting. This is the probability distribution that was calculated on our output layer for, these, for that image. So if we want to figure out what class we actually think that this is predicting for, we can use a cool function from NumPy called argmax, which essentially is just going to take the index. This is going to return to us the index of the maximum value in this list. So let's say that it was, I'm looking for the least negative, which I believe is this. So this should be 9. This should return to us 9 because this is the index of the highest value in this list, unless I'm just wrong when I'm looking at the negatives here. So 9, that's what we got. Okay, so now if we want to see what the actual class is, Well, we have our class names up here, so we know class 9 is actually ankle boot. So let's see if this is actually an ankle boot. So I'm just going to do class underscore names. I think that's what I called it, like this. So that should print out what it thinks it is. Yeah, class underscore names. But now let's actually show the image of this prediction. So to do that, I'm just going to steal some code from here because I don't remember all the syntax off the top of my head. So this. So let's steal this figure. Let's show this and let's see if it actually looks like an ankle boot. So to do that, we're going to say test underscore images 0, because obviously image 0 corresponds to prediction 0. And now we'll show this and see what we get. Okay, so ankle boot, and we'll be looking at that. The image is actually an ankle boot. And we can do this for any of the images that we want, right? So if I do prediction 1, now let's have a look. Pullover, it kind of looks like a pullover to me. I mean, I don't know if it actually is, but that's what it looks like. We can do 2. Let's have a look here. Okay, trouser. Yep, looks like trousers to me. And we can see that that is how we get the predictions from our model. We use model.predict. All right, so let's move down here now to the next thing that we did. All right, so we've already done that. So verifying predictions. Okay, so this is actually a cool kind of script that I wrote. I'll zoom out a little bit so we can read it. What this does is let us use our model to actually make, and I've stolen some of this from TensorFlow, to make predictions on any entry that we want. So what it's going to do is ask us to type in some number. We're going to type in that number. It's going to find that image in the test data set. It's going to make a prediction on that from the model and then show us what it actually is versus what it was predicted being. Now, I just need to actually run, actually, let's just steal this code and bring it in the other one because I've already trained the model there so we don't have to wait again. So let's go F11, let's go to a new code block and run that. So let's run this script. Have a look down here. So pick a number. We'll pick some number. Let's go 45. And then what it's going to do is say expected sneaker, guess sneaker, and actually show us the image that's there. So we can see this is what, our pixel kind of data looks like. And this is what the expected was. And this is what the guess was from the neural network. Now we can do the same thing if we run it again. Pick a number 34. Let's see here, expected bag, guess bag. So that's kind of showing you how we can actually use this model. So anyways, that has been it for this kind of module on neural networks. Now I did this in about an hour. I'm hoping I explained a good amount, that you guys understand now how neural networks work. In the next module, we're going to move on to convolutional neural networks, which again should help, kind of get your understanding of neural networks up, as well as learn how we can do deep computer vision, object recognition, and detection using convolutional neural networks. So with that being said, let's get into the next module.